appreciate you coming here tonight. It's a fun invitation. I see a huge crowd. I see several familiar faces. It's fun to see many of you, and hopefully we can catch up afterwards. What we're going to talk about today is really work of my students, Joseph Gonzalez, Yucheng Low, Aapo Kyrola, Jay Gu, and Joseph Bradley, and my postdoc, Danny Bickson. And for the last 4 years or so, a little bit more, we've been working on how do we scale up machine learning algorithms to huge data sets, which now are called big data sets only. Big data, using cloud computing. And we developed a system called GraphLab that's gotten a lot of traction in the industry and a lot of people are excited about. So I'm happy to come and talk to you about it and hopefully get feedback from you. So needless to say, the scale of data is growing tremendously. Be it images on Flickr, users on Facebook, or the 72 hours of video uploaded every minute to YouTube that nobody's going to watch. And this move towards huge data sets is such a buzz that about 6 months ago there was an article in the New York Times that said big data is a new economic asset like currency or gold. And exactly. And so for it to be an economic asset, you have to unleash some value from it. And in a biased way, I'll say the only way to unleash value is to use machine learning. And the question is, how do you do machine learning in the context of these new parallel architectures, be it GPUs, multi-cores, clusters, or the cloud? And the problem is that people that work on machine learning for many years, like me, have no clue how to write parallel programs. And if I'm honest, in my group, it's really my graduate students, end up addressing the same parallel problems again and again and again. Race conditions, distributed state, race conditions, communication, race conditions. And you end up with code that nobody can understand, nobody can debug, nobody can extend, and it just gets thrown out, basically. And because of those reasons, we've moved towards higher level abstractions that make it easier to program parallel machines. Perhaps a common abstraction today is one for data parallelism, MapReduce. And this is good for basically independent subproblems. So let's say they have 6 billion images on Flickr. I could send images independently to different machines and use those to detect faces, for example. These are independent subproblems, so MapReduce is quite good for those. And the question that we started asking maybe 5 years ago is, what fits into this framework and what doesn't? So is there more to machine learning than detecting faces on images, what's called feature extraction? And the claim is yes, and I'm going to show you through a cartoon example. If I show this patch of a big image and ask you what it is, what would you say? Mars, I like Mars, yeah. It's hard to tell. If I tell you it's near this other patch, you might start getting a clue. But if I show you the big picture, it becomes obvious. So I would say that the power of the value of big data is in dependencies. It's the power of dependencies. And in machine learning, we represent the dependencies using graphs. So let's talk about a few examples of graphs. Let's say that I have a database of images and I label this picture as being my grandmother's. I want to propagate this information through my database. And I end up hitting this other image whose similarity is not very strong. So I might not be able to make a prediction with just one image. But what I can do is find other images in my database that are similar and form a graph among similar faces. And I can also use other information. For example, people who co-occur images together tend to be friends or from the same family, and they co-occur in other pictures. So if I form a graph of these relationships, I can propagate the information in this graph and make a better prediction. This is just an example of building graphs in data. There are many other examples. One that we're all familiar with is collaborative filtering. Let's say you have a user whose favorite movie is Women on the Verge of a Nervous Breakdown. Why are you laughing? It's a great movie. It's a very good movie. Who also likes The Celebration, City of God, and Wild Strawberries. What else would you recommend for this user? It might be hard, but thankfully, there are other users with similar idiosyncratic tastes who might like those movies and maybe also like movies such as La Dolce Vita, And so Double-Data Chavita might be a good recommendation. So here's a graph between users and products, users and movies, users and songs. Finally, my last example is a graph between text documents. So you could, for example, link books to words that appear in those books and form a graph like this. And using a technique called supervised learning, you can detect automatically there are certain topics that appear in those documents. For example, some are about apples, some are about computers, and especially if this was YouTube videos, there'll be this huge topic about cats. And so if you run this on Wikipedia data, you discover, for example, that there is a topic about colors, there's a topic about cars, and there's one about war and so on. So this is the type of things that we might want to do with data. What does that pipeline look like? We typically start from data, be images or text. We do some feature extraction, for example, detect faces or important words, and we connect them together into graphs, for example, among similar faces or shared words. And then we do this magic, which we call structured machine learning algorithms. They do some kind of processing in this graph that hopefully extract some value from data. The blue boxes on the left are relatively well understood, and they often fit well with data parallel abstractions, such as MapReduce, and we call that the graph ingress problem. The purple box, on the other hand, is harder to deal with. We call those graph structure computations, and that's what we're going to talk about today. That's the focus of our work. So if you go back to that picture, is there more to machine learning? There's certain techniques that fall onto the right side. For example, for those familiar with those, graphical models, semi-supervised learning, collaborative filtering, graph analytics. Many of those techniques don't fall well into MapReduce and fit well into some other abstractions that we're going to talk about today. So let's start with an example, running example of graph parallelism. And we use the simple page rank algorithm. Let's say that I have a social network and I want to figure out who to advertise to. And it depends, for example, on the rank of the user in the social network. So I ask, what is the rank of this user? I don't know, but it depends on the rank of the users who follow her. What are their ranks? I don't know, but it depends on the ranks of the users who follow them. And you end up with a graph with cycles, and since this graph is a cycle, somehow you iterate some algorithm until you converge. For example, in page rank, you say, my rank is the weighted average of my neighbor's ranks. My rank is the weighted average of my neighbor's ranks. And this will converge to some interesting prediction. This is an example of a graph algorithm. Graph algorithms start with a graph over data. They write some local update functions. For example, my rank is the weighted average of my neighbor's ranks. And you iterate those until convergence. Turns out that MapReduce is not a good solution for this. And you need what's called a graph parallel abstraction. So, since this is a geek crowd, I can talk a little bit about one of the questions that comes up when you're building such abstractions, which is the issue of synchronous versus asynchronous computation. So, a basic model for graph computation is the bulk synchronous model BSP of Valiant from about 20 years ago. So a Turing Award when talking about ACM. So the model is very simple. You have a graph. You intuitively assign a processing unit to each node in the graph. And you do some thinking. And after everybody's done thinking, you talk to your neighbors. You talk to all of your neighbors. And when you're done talking to your neighbors, you iterate. So you can imagine a process where you think in your head, you turn left and right, you talk to people, and then you repeat that. Turns out that this bulk synchronous model, BSP, is highly inefficient for a variety of reasons. So from a systems perspective, you have the same curse that you have with MapReduce, the so-called curse of the slow job. So if you have a slow job along the way, the overall running time is dictated by the time of the slowest job in every iteration. And this can really significantly slow down your process. So this is maybe a systems question. But there's also some really hard machine learning issues that show up. So for example, a graph of dependencies, in a graph of dependencies, not every dependency is the same. There might be some embedded sequential structure where the questions are at, where the hard questions are at. And you have to prioritize your computations to focus on this area, but you don't know where the areas are going to be until you start thinking. And so you want to focus dynamically on your computation. Let me show you a cartoon example of that. So I've taken an image and I added some noise to it, and I'm forming a graph among neighboring pixels in order to remove noise from this image. And if you think about it, the hard parts of this prediction are among the borders between different colors in this image. If you use a smart algorithm, this is what it will do. First, it will do updates everywhere. It will think everywhere, like a both synchronous model. But soon it will discover there were some hard parts of the problem and focus its computation only where it's hard. And this is what you want to be able to do. This is hard to do with MapReduce. This is hard to do with the bulk synchronous model, which is implemented by Pregel, for example. And so this result that we had from the machine learning side from about 5 years ago was quite interesting. What it showed is, for example, in practice, if you increase the number of processors in the x-axis and you look at the running time of a machine learning algorithm, if you use the bulk synchronous model of Valiant, you end up with a perfect scaling. So as you add processors, it gets better and better. But you're scaling a slow algorithm, which is kind of a useless thing to do. In fact, if you compare that to an asynchronous algorithm with one processor is faster than this bulk synchronous model of 8 processors. And this is not just a practical issue, this is a theorem. So about 5 or 6 years ago, we hit this result, and being a more theoretical person in machine learning at the time, we thought, okay, let's implement these algorithms. And here's where the truth in advertising came through. Building the systems, distributed systems to implement these algorithms was just painful, slow, and ridiculously useless. And we ended up having to build a system of our own to be able to support these distributed asynchronous algorithms. And in one of those interesting turns of life, very few people remember those original algorithms that we had, but a ton of people are using the system that we built to support those algorithms for other things. So it turns out that the system perhaps was more important than the actual algorithms that we developed. And this was the birth of the GraphLab project. So developing systems that support these large-scale distributed algorithms for machine learning, or computations on graphs. You can also view it that way. So the idea here is that somebody like me that knows how to solve a problem, say on MATLAB in one processor, GraphLab would feel a dream where you come in and say, I know how to solve the problem in one machine, feed it to GraphLab, put it on Amazon AWS, and you automatically get large-scale parallel predictions. That's where we're going. That's our effort. So let me talk about first the first version of GraphLab, GraphLab 1. So in GraphLab 1, we started with graphs of data. So for example, a graph might be a social network graph with data in the vertices, like a user's profile, and data in the edges, like, for example, similarity weights between neighboring users. And we want to do some computation on this graph. So the question is, how do you do computations on graphs? How do you write graph programs? And one way to write graph programs is to think like a vertex. And my question to you is, how does a vertex think? And my thought is that a vertex thinks by looking at itself and its neighboring edges and neighboring vertices. So if we go back to the PageRank example, you might look at the current rank of its neighbors. Then you say, my rank is the weighted average of my neighbors' ranks. And by the way, if my answer has changed by a sufficient amount, I go back and tell my neighbors that they might have to recompute their value. And this is an example of dynamic computation, of that asynchrony that we discussed in the beginning. Simple example of that. So GraphLab allows you to write programs like this, to think like a vertex, and it automatically parallelizes and prioritizes computations in an asynchronous way. And as you're doing that, you can hit some of those initial problems in parallel computing. One of them is race conditions, the famous race conditions. So if the red vertices are executing in parallel, and somehow the blue vertex in the middle starts executing, the scope of their data overlaps. So one vertex might write to data, the other is a reading. And this is called a race condition. And when I started this project, people told me, oh, you work on machine learning. These are all statistical methods. Who cares about race conditions? You should just run and hope for the best. What they were telling me is that if you ignore consistency, you're going to have higher throughput, more updates per second, which is true. But you could have slower convergence and even divergence in your solution. So let me show you an example of that. In the x-axis, I'm looking at, you can think about it, wall clock time. As the algorithm is running, in the y-axis is the error of the algorithm. Lower is better. We're looking at predictions on Netflix data and using only 8 cores. If you don't guarantee consistency, this is the kind of behavior that you get. If you guarantee consistent updates, this is the behavior that you get. So it quickly converges to the right answer. This is not the case. This is a bit of an extreme example. It's not the case on every algorithm. In some algorithms, consistency is important. For others, it's not. And what GraphLab does is allow you to turn consistency on and off in a user-specified way. So that was where we were in GraphLab 1. GraphLab 1 was about a year ago, maybe. And so what you did was write a program by specifying a graph among your data, update functions that modify vertices and neighboring vertices, schedulers for asynchrony and consistency models. And this got picked up by a lot of people. Lots of algorithms were written on top of GraphLab for a variety of machine learning problems. So let me give you an example of one of those. Tom Mitchell's group at Carnegie Mellon wanted to solve a very large-scale natural language processing question. And their methods were not scaling on a single machine. They weren't able to solve on a single machine. So they started using a cluster in Hadoop. And the problem they couldn't solve before, now they could solve with Hadoop using 95 cores in only 7.5 hours, which was reassuring for them, was good. But then they looked into GraphLab, and the same problem on 32 EC2 machines was solved in 80 seconds. So this is 0.3% of Hadoop time. So again, we were feeling quite good about ourselves at that point, maybe a little too good, a little too cocky maybe. And we tried to say, okay, let's find the biggest graph we can download. And it's hard to, in academia, it's hard to have access to certain data sets. But we looked around, and there was this web graph from Alta Vista. They had about 7 billion edges. And we said, there's no published results in academia on this type of graph. Let's run GraphLab and show them how it's done. And we failed. In a sense that it was not scaling well, the performance was poor, it wasn't beating other systems. We were disappointed. And we decided to go and investigate what was happening. And what was happening is that these web graphs and another phenomena come up from real world phenomena for what's called natural graphs. And natural graphs are very interesting. They have properties which are not well captured by most, if not all, graph abstractions out there. And the issue is that systems like GraphLab 1, Pregel, or those in high performance computing typically assume the graphs are more or less uniform. They have low or small degree vertices which are easy to partition. Natural graphs are nothing like that. They have some very high degree vertices. In fact, the degree distribution tends to be power law, which makes them very hard to partition and very hard to deal with. So just to give you a sense of that, here I'm looking at the web graph from 2002. The x-axis I'm showing the degree of vertices, the y-axis the number of vertices, and you can see that the top 1% of the vertices are adjacent to 50% of the edges. So, you know, this might be Google or one of your companies, and up here on the left is Carlos Guestrin. And I guess everybody's pushing to the right. So this is a very, very high degree graph. And the web graph is not the only one that has these characteristics. If you take a social network, you can have a very popular person who's connected to many, many people in the graph. In a movie recommendation system, you can have a very popular movie that many people rated. In machine learning problems, you have these things called hyperparameters which are connected to every vertex in the graph. And in text analysis approaches, you have common words that appear in many, many documents. And this issue is very problematic because it leads to star-like motifs, where you have a vertex with many, many connections, And the number of those vertices can be quite large. And that can create problems for pretty much every system out there. And the issue here, or one issue, is that if you try to partition your data among machines, what you end up doing is cutting a lot of edges. And the computation that you're doing is linear in the number of edges cut. And even if you could solve the NP-hard problem of cutting these natural graphs, the cuts that you get will not be cheap. And so, and popular techniques like methods for cutting graphs don't work well. And for these reasons, systems like GraphLab and Pregel use what are called hashed partitions, which is just a fancy word to say they randomly assign vertices to machines. And proof by PowerPoint, a lot of edges get cut. In fact, here's my little theorem for today. If you have P machines, 1 minus 1 over P of the edges get cut. So if 10 machines, you're cutting 90% of the edges. If 100 machines, you're cutting 99% of the edges. So since you have to move every piece of data anyway, you might as well use MapReduce. There's no point in using anything else. And this realization led us to GraphLab 2, latest version of GraphLab, which starts from the place that we were before, but instead of cutting edges, it ends up cutting high-degree vertices, or vertices in general across machines. And this is a direct consequence of a new type of graph computing abstraction, where you still think like a vertex, you still program as if you were on the left side of the slide, but it gets executed in a distributed way as if you're on the right side of the slide. Now, this is the only little bit of technical stuff they're going to do. I'm going to talk a little bit about what this looks like. So if you start with a PageRank example from before, you can divide the computation into 3 phases. First, I'm gathering information about my neighbors. What is your rank? And adding it together. Then I'm doing a local apply. I'm changing my rank as the weighted average of your ranks. And then I do what I call scatter, where I take and I tell my neighbors, you should go and recompute yourself. So PageRank splits the computation into 3 phases, the gather, apply, and scatter phase. So GraphLab 2 abstraction does exactly that. The gather phase is like a reduce over neighboring vertices in a commutative associative fashion, which then gets used to change the center node's value, myself, and then leads to a scatter, data parallel computation over the neighboring vertices and edges. So this is the abstraction for GraphLab 2, and it turns out that many machine learning algorithms from graph analytics, inferencing graphical models, matrix factorization, collaborative filtering, and others fit well into this GAS model. So what I'm going to do now is take a little breather and talk about one very simple application of these ideas in social networking, and I'll use it to illustrate a very much trivial way of doing gather, apply, scatter. So let's say that I have a social network and I want to figure out who to advertise to. The most obvious thing is to advertise to people who have many followers, who have high degree. But what advertisers have found is that these people might have high degree, but they're not part of strong communities. Today, this is a strong community. If I tell some of you, you tell each other, and there'd be a spread well between this community. So another metric that was used quite a lot is the number of triangles somebody's part of. Somebody who's part of many triangles, that is 3-way relationships. I know somebody, say I don't know Mary, Mary knows John, and I also know John. So if I'm part of many triangles, it turns out that I'm part of a more cohesive community, it's better to advertise to me. So how do we count the number of triangles a user is in this gather, apply, scatter model? It's a trivial program. In the gather phase, I just go over my neighbors and I collect what their IDs are. And I just save those. And in the scatter phase, it's like the game. I guess it's different in the US than what I played as a kid, but we had these cards for football, the one that you play with your feet, let's say. And you would have the cards, and we get together and we compare the cards and we figure out which ones we have in common, which ones have difference, so we can exchange that. So it's the same thing here in the scatter phase. I take my neighbors and I compare them to you and say, oh, we're both neighbors with Mary, so we're part of at least one triangle, and you can count triangles those ways. And that's a scatter phase. So, very simple program. If you look at the Twitter graph from 2010, you get already an interesting behavior. If you look at who has most followers then, it was Britney Spears. But who's part of most triangles or strong triangle community, you get people like Stephen Colbert. And that's very interesting because Stephen Colbert is able to do so many things by mobilizing his community, like change truth in Wikipedia. So going back, we built a scatter model by thinking about this new graph partitioning problem, where actually we're splitting vertices across machines rather than cutting edges. And now the communication is linear in the number of machines spanned by a vertex. This is called the vertex cut problem. And percolation theory suggests that it's possible to come up with cheap vertex cuts even for natural graphs. And GraphLab includes a fast online cutting algorithm for these types of cuts with some theoretical guarantees, and it works really well. So, I talked about GraphLab in an abstract way, but GraphLab is really a system that's actively used out there. It's built on top of standard cloud infrastructure that most of you are familiar with. And it provides a bunch of boxes that allow you to do the kinds of things that I talked about, but you can ignore those in a sense that there is a very clean API for programming over graphs. And so you can write to the API, or you can write to one of the existing toolboxes. So a number of people in my group and in other groups around there have released code on top of GraphLab that does a bunch of machine learning tasks, like graph analytics, graph models, computer vision, clustering, topic modeling for text analysis, and collaborative filtering. In fact, most users today of GraphLab use it for collaborative filtering tasks. So this is a way to get very large-scale machine learning accessible to you or your company. So let me show you a couple of performance metrics. If you look back to the triangle counting problem in the Twitter graph, there were 34 billion triangles to be counted in 2010. And there was a paper published over this data set where they used Hadoop. This was the fastest available procedure for this. And on about 1,000 machines, it took them about 400 minutes to compute these triangles. If you use GraphLab 2, on 64 machines, it takes you a minute and a half. And the issue here is not just that GraphLab is a great piece of software, which I think it is, but it is also a question of abstraction. Turns out if you write this code with MapReduce, you're doing degree-squared communications per vertex, which can be a real killer here. Now, running time is one measure of productivity, but there are other measures of productivity. So another measure is programmer's time. So let's talk about text analysis. I showed you that Wikipedia example at the beginning. That's an example of a topic modeling algorithm. And these algorithms are quite widely used in practice. So topic modeling is quite useful in practice for building recommendation systems. So for example, for figuring out what to put on the front page of a news provider, or what ads to serve on a particular web page. And because of that, lots of companies have implemented this type of technique. So for example, at Yahoo, Alex Mola built this really, really cool and beautiful system just for this task. And with 100 Yahoo machines, he can process 150 million tokens per second. That is fast. With GraphLab 2, we process on 64 machines about 110 million tokens per second. The difference is this first system was built specifically for this task, and it was engineered just for this problem. GraphLab 2, it took my students 4 hours and 200 lines of code to implement this algorithm. So in terms of productivity, it makes a huge difference. The third measure of value might be money. And if you're solving, for example, PageRank on that Twitter graph, if you use Hadoop, it takes about 5.5 hours. If you use an in-memory version of MapReduce, it takes about an hour. If you use GraphLab, it takes about 8 minutes. So if you're paying for computation, the first one costs you $180, Hadoop. Twister costs you $41, and GraphLab costs you $12. So we can go back to the graph that was stomping us, the one that did not have published running times with 7 billion edges. And now we can run it on AWS with 64 machines, about 1,000 cores and 4 terabytes of RAM. And we process one iteration over the graph in 7 seconds. So that's 1 billion links processed per second. And that's 30 lines of user code. So at this point, we're again feeling good about ourselves. And then my student, Aapo Kyrola, walks into my office and says, buy me a Mac Mini. And I think he wants to watch TV. But he said, no. I want to build a small version of GraphLab that can solve web-scale problems on any machine, on any computer. Now, there's always a genesis stories for things, which may or may not be true. And there's also a genesis story for names, which may or may not be true. So there's the question is, where does the name GraphLab come from? And a lot of cloud-based systems have animal mascots. And I had a dog, a Labrador, so that was GraphLab. And Aapo wanted to build a small version of GraphLab, so he called it GraphChi, for Graph Chihuahua. And he told me, I can solve web-scale problems by exploiting SSDs or hard drives. And the challenge with that is that random accesses to data can be quite costly. So graphs are hard to lay out on disk. And if you have to seek different parts of the disk for different pieces of the graph, that can be extremely slow. And so what Aapo developed was a novel solution which he calls parallel sliding windows method, which minimizes the number of random accesses. I'm not going to have time to go into detail, but let me just tease you with an example of performance. If you go back to the triangle counting problem, which on 1,000 Hadoop machines took about 400 minutes, on 64 machines took GraphLab to about 1.5 minutes, Aapo can solve this on a Mac Mini in 59 minutes. It's pretty impressive.
The only reason I'm not laughing is because I'm still doing what to do.
Okay. Thank you. So let me tell you where we're going with this. Today, GraphLab, Hadoop, and many other cloud infrastructures are built for batch computation. In other words, you take a graph, for example, give it to GraphLab, you get some predictions back. But that's not how the world works. If you think about Facebook's graph, new users are arriving all the time, so verts are being added. People are friending people, so edges being added. People are defriending people. Thanks, Natalia. So edges are being deleted. And so what you should be thinking about is not GraphLab as a batch system, but GraphLab as a database. In a sense, the data is arriving all the time, and a stream of queries is arriving, and you want to make online predictions. So this is where we're going. Our first step in this direction was to do this in the context of GraphChi, where we can stream in data from Twitter at about 100,000 edges per second to a Mac Mini, at the same time as we're processing 200,000 edges per second in terms of computation. So just to close, GraphLab is a system that provides an abstraction for very, very large graph computations. You can access through the abstraction, or you can use one of the toolbox for large-scale machine learning. And it is available today in an Apache license in open source at graphlab.org. Thank you. Now I take time for questions. Yes.
So I was just wondering that sometimes, like here you showed mostly how fast it can do something like determining number of triangles and stuff in the network. But when there are non-deterministic solutions to some machine learning supervised learning problems, do you have a facility to optimize for something else, like accuracy, or is it always?
I see. So the question is, I'm going to abstract your question a little bit, so that it's a little bit more broad. The question is, you can optimize machine learning algorithms for running time. You can make them faster for the same solution, or you can keep the running time fixed and make the algorithm more accurate. For example, this is two extremes in some spectrum, and the question was, can you walk that spectrum? And the way to think about this is that GraphLab is a system that supports machine learning. So there are many algorithms that try to walk that spectrum. What GraphLab enables you to do is to solve it closer to the more accurate spectrum if that's what you want. So in terms of collaborative filtering, for example, the way typical algorithms work is that they represent users in terms of what categories they're interested in. And if you use GraphLab for the same running time, you could use many, many more categories and get more accurate solutions. So you have that choice within the system. So speed enables more accuracy. That's another way to think about it. There's a question over here.
What do you use for persisting the data? Do you have some specific format, or you use files, or what?
Good question. So the question is, there's two questions embedded in it. I just want to clarify. Is this for robustness or just for outputting?
I think persisting graphs is a pretty hard problem, so I'm just curious.
I see. So how do we store our data, in a sense, is the question. We have our own format and a kind of own way to write data. It's not too surprising. You can look at the specs. The way the next generation of GraphLab is working, the way it's being developed, I just give you a hint at the end, the format is going to be more open. There's more open access, so you could use it for other things in addition to GraphLab.
Do you use some persistent store, or you just...
During computation, the graph is in memory. The data is in memory across the cluster, except for GraphChi, where the data is in disk is run up. For GraphChi, the data is stored in a proprietary format during the computation, but the way it's input and output is through standard data formats that you can imagine. Okay.
Is there any, like, for people that do like the deep learning with like neural networks, is there any way to like take advantage of a GPU on each node?
I see. The question is, two questions here. For people who do deep learning, is this useful? Yes. People have done deep learning type models in GraphLab. Can you use GPUs with GraphLab is another question. We haven't really done that. You could try. GPUs have limitations and have advantages. We haven't really walked that spectrum.
Very little shared local memory.
Exactly. So it's hard to deal with non-dense problems in GPUs. But they're getting better. So, and the architecture is getting better too. So it's interesting to think about how they will be in the future and what the GPUs look like in 5 years, for example. I don't know. Yes?
You still need to do vertex splitting in the Macintosh in GraphChi?
What's that?
You still need to do vertex
splitting
splitting
in
in GraphChi.
Okay, good question. Well, GraphChi runs on any machine, not just a Macintosh. That's a kind of a rhetoric in a sense. So do we have to do vertex splitting? In the shared memory case, which is where GraphChi is running on a single machine, the situation is a little different, so you don't have to think about it that way. But as we're pushing GraphLab to its new version, it kind of blends GraphChi and GraphLab, so there's no distinction between the cluster with disks and a single machine with disks. So there will be vertex splitting in that setting. But it's all done automatically by GraphLab, whether or not you do.
So you split across windows, I guess.
Yeah,
Okay.
exactly. Actually, that's how GraphChi works. In a way. Yes?
This is along the same lines. The gather applies scatter is literally a MapReduce program where the map is the scatter, preserving data locality for the node.
Right.
And the gather applies is reduce for that node.
Right. So the question is, the difference though with MapReduce is that MapReduce is a global computation, right? So it goes over everything. What I'm saying is that you can write your vertex programs in a sense as a MapReduce style computation over its neighbors. So use the same kind of primitive ideas, but it's in a different setting, if that's clear to you. Yeah, that's why when I described the gatherplex scatter model, I said you do a reduce over neighbors, and then you do a scatter over neighbors, really a transform. It's not a reduce, but it's on your map.
Yeah. The scatter is the map preserving data locality.
Yeah, exactly. Yes, it's super. I think the one person before had the hand.
I have a question about the future and
Question about the future. Good thing you have a machine learning person here. I will predict the future for you. Tell me.
when we talk about real-time processing, the data will arrive in do you have a plans for converting the data into graph data, or
Okay.
it has to be done by somebody who designs the system of streaming or incorporating the other systems?
Okay, very, very good question. So I don't know if you guys heard from this side, but I'll just repeat it briefly. In the online setting, as new data is arriving, do we have support for transforming data formats, for example, and interpreting them as graphs? This question is also true even in the batch setting. How do you go from raw data to graphs, that first two boxes? And the answer is we have currently some infrastructure for doing that, and we have a collaboration with Intel where they're building more infrastructure for that problem. So for those blue boxes. So there's some already there present. There's a project that spun out of our group that now Intel is doing, which is called Graph Builder, that does more of that. But there'll be more in the future. So more in the future. Yes. So also, yes.
Yeah. So your GraphChi, the data is a flat noise on the SSD. So what the data is in the memory? How much more performance gain do you expect?
So if the data is in memory, then you're back to GraphLab. GraphLab on one machine and GraphChi in one machine is the same thing in a sense. The question is how much data can you fit in memory on one machine? So GraphChi only kind of makes sense if you have problems that don't fit in memory on one machine.
So what you are saying really, you only need one computer, just huge memory.
Okay. So the question is, if I want to solve web scale problems, can I use just one computer with huge memory? And the truth is, one computer with huge memory will go a long way for a lot of the problems that I'm sure all of your company want to solve. But the hard part of it is that you don't get as much parallelism, let's say. Like it's easier to scale out memory than to put more processors on machines today. But it's surprising what you can do with one machine with enough memory. With some abstraction like GraphLab, let's say. Yes.
Have you looked at using your basic approach for something like hardware simulation?
Yeah, so we have not used it for hardware simulation. It's pretty natural we got in that question before since it's a graph problem and you want to do stuff with it. But I'm sure.
Knock yourself out.
Knock yourself out, exactly. I don't know anything about hardware, so I don't know what to say about that.
So you mentioned, so looks like the system is targeted towards the graph-based algorithms. You mentioned some others there, like tensor factorization. So how do you present them in the GraphChi, or if there are any other uses of your system besides classic graph problems?
Tensor factorization is a graph problem.
It is.
Yeah, because the way to think about it is matrix factorization, which is a collaborative filtering basic case, you have users by movies. Mm-hmm. Tensor factorization, you have more dimensions. You have, for example, users by movies, by products they bought, by pages they clicked, by whatever. And that tensor, which is really this multidimensional array, is a sparse object. Because not everybody has rated every movie, has bought every product, has done everything. And so the sparsity of that is the graph. So you can think about it as complex algorithms over sparse matrices, as one example. Does that help?
Yeah.
Thanks. There were a couple questions.
My question is along similar lines. So collaborative filtering is one algorithm which we use a lot. So are there any couple of other examples of algorithms which you can, let's say SVM or so?
So things that today, so question is like, what are other things that GraphLab is being used for? So collaborative filtering is, I'd say 50% of the users of GraphLab today use it for collaborative filtering type problems. And that's a broad stroke, it's not just one algorithm. Different things like, different companies around here of large and small. Then the next one is for social network analytics type problems. So community detection, clustering, detecting communities. You guys are working on ads is a very natural place for it. Some people working on ads are doing that, especially when they want to advertise to social networks and that kind of thing. Then after that is text problems. So things like how do you interpret and detect structure in web pages? For example, not just one web page in isolation, but connecting to other thousands of web pages. Again, in the context of ads, how do you provide ads that are specific to a particular web page by looking at more structure in that problem. And then after that, the tail is like longer, I would say, as to what people do. There was a question here before.
In the Pregel paper, they talked about where you co-located nodes, but they left it as an exercise up to the reader. So that's a pretty important topic. Does GraphLab offer any possibility for GraphLab to optimize, where nodes are placed to improve performance?
Where data is placed? Yeah. So the question is to this side of the room. In the Pregel paper, page 7, paragraph 2 or something, they say how do you place data is left to an exercise for the reader. In our paper, that's an integral part of the system. When I described GraphLab 2, I talked about data partitioning and graph separators or vertex separators. And so part of the system includes an algorithm that optimizes how data is placed in the network.
And does that also optimize over, I meant by the history, if you had GraphLab looking at a history of a graph and the computation against it, could it learn and then balance things out differently?
Okay, so GraphLab as it stands today is a batch processing system. So it doesn't remember the past in a way. But in GraphLab 3, the online version, the graph will live forever. And so in that case, it's where it makes most sense to do this re-optimizing of data. And that's exactly in the design specs that we're building today. But that's a great question. And clearly you know the details of the more deeply, yes.
How about the types of data you can put? Does it support attributes, how strong type it is, where you can put the data?
GraphLab today is written in C++. GraphChi is written in C++ and Java, and it supports whatever magic thing you want to do. In a sense, it is strongly typed, but it's typed as you wish. So your vertex data can be anything, your edge data can be anything. It can even be mutable and change over time.
It's mutable or immutable?
Mutable.
And so what happens if you put everything and run algorithms which don't find the stuff, right? So the point is, I think there is a tension between how strong types you make it versus how flexible. So I'm just curious.
Right. Okay, so the question is between typing and flexibility, and I'm so with you. So one of the downsides of GraphLab today, if I'm honest, is that it was a system built for our group to do something, and then people started using it. So we were building lots of C++ code, and we were happy with it. But in the long run, I think there is a trade-off between programmability, what you call flexibility, let's say programmability, and the performance of strong typing. And what we're doing with the new version of GraphLab is making that a little more flexible. It's not all flexible like Python where you can just do anything, but there's a lot more flexibility with respect to types.
Like to give the strong typing is a better choice if you ask me.
For you?
Because it enforces a bunch of rules, makes it difficult to break, right?
Yeah. Strong type, yeah, no, this is the ACM chapter. We can argue about strong type. I love it. I would say...
welcome home.
I'm fortunate enough to be in a academic department, well, my second academic, third, fourth, and to have that daily opportunity to argue with the PL people, programming language people about typing versus not typing and so on, but it's fun. There was another question, yes?
So I saw on one of your slides you listed GIP sampling as one of the examples you support. Can you elaborate on how you parallel GIP sampling?
Sure. So, well, that's good. How do we parallelize GIP sampling? We're doing GIP sampling over graphical models. So that could be conditional random fields, Markov networks, Bayesian networks. And a trivial way of parallelizing GIP sampling is to do multiple chains in parallel. But that's not what we support that you can do easily with MapReduce. What we do is parallelize the updates within a graph. And so the consistency model with GraphLab guarantees that you're able to get correct answers and sample vertices that don't overlap at any time. And so you still have the same convergence guarantees as standard GIP sampling. So that's a long technical winded answer, but I'm happy to kind of go into a lot more detail with you. Yes?
So has anybody implemented like named entity recognition like with a CRF or?
Has anybody implemented named entity recognition with a CRF? So named entity recognition per se, I don't know of cases, but For example, the Tom Mitchell's group example, what they want to do is figure out in a very weakly supervised way that, say, San Jose is a city, Carlos Guestrin is a person, and eBay is a company. And they build a graph of sentences of where Carlos Guestrin co-occurred with certain other words, and they propagate information in that graph in order to make predictions. And they've got really good performance. That was the example they reported from their group. But for name identity recognition CRFs, I don't know what has been done.
Who was that did that?
Tom Mitchell.
Tom Mitchell.
Yes, sir.
So the assignment of the node to the machine, is it static or it changes as the data is going?
The question is, this assignment to the node to machine static, or does it change over time? This is exactly, in a sense, the same question that was asked over here. And today, in GraphLab, the assignment is static. But in the new version of GraphLab, where the graph will live forever, you're going to have the assignment potentially change over time, because the structure of the graph might change over time. Yes, sir.
Have you experimented with having large virtual address spaces per real address space?
Oh, I see. So you're saying something like distributed RAM or something like that?
Well, no, where you're using paging as opposed to having fixed size.
Oh, I see. Paging to disk, you're saying. Did we try, question is, did we try large address spaces and paging things to disk? If you do that, you end up with the loss of random access problem that GraphChi solves in a way. So the way to think about GraphChi maybe is a smart paging strategy, if you want to think about that way, where it figures out what should be which should be in the same page and what should be loaded when. That's one. I haven't thought about that, but what's one interpretation of that approach? Any other questions? Okay, well, thank you very much for taking the time. Oh, well, I'll catch you at the end, unless you want to ask them. Go ahead.
I was just going to ask if you altered the Mac Mini at all.
Did we alter the Mac Mini at all to get those results? Yes, we put 7 processors inside. See, a Mac Mini is like, so, you know, it's like when you go to In-N-Out Burger and you can ask for like whatever number of patties. We did that with Mac Mini. So the answer is no. We did turn off the caching of the OS caching so that we can directly figure out what pages come in and out. But other than that, we didn't change it anywhere.
So you use all your processors?
No, Mac Mini has 2 processors. 2 processors.
So it's still kind of distributed.
It is still some parallelism, but there's very little parallelism. Okay, well, thank you very much.